A very warm welcome and thank you for joining Isifundi training for our bite-sized corrosion. During our April series, we've been looking at corrosion failures. We know that when we have a corrosion failure, we're always desperate to clean up the mess and get things back the way they were. But in that, we can often destroy the evidence of what caused the failure, and that can be a disadvantage in letting us figure out the problem and preventing it from happening in the future. If you've missed it, our discussion with Neil Webb focused on exactly that and why it's important to make sure that we gather as much evidence as we can. And then we continued our discussion with Rolf Mustert looking at how the environment can cause corrosion, as we're looking at environmentally assisted corrosion. Today, I'm delighted to welcome back Melanie Smit from Mintek. Yesterday, Melanie and I started our conversation looking at some corrosion failures which were rather localized in mechanism. And today, Melanie and I are going to be looking at some more general corrosion failures. And hopefully we'll get to discussing some practical methods of testing materials when we want to subject them to new environments. So welcome back, Melanie. Thank you for coming again. Melanie, yesterday we spoke about crevice corrosion. We briefly touched on pitting corrosion and how a small pit can be like a really disaster happening underneath the surface. And then we focused on some corrosion bursts, particularly of boiler tubes. But we've also seen that the environment can also cause a bigger problem with the corrosion than just at one space. So let's talk about how in a bigger environment we can have corrosion.
Hi, everyone. Yes, I wanted to kind of go into one of the most unpredictable or, let's say, unexpected types of corrosion that we've seen quite a lot of. Most of you will be familiar with it, stress corrosion cracking. It's a failure that occurs for a specific susceptible material in a specific environment where tensile stress is also present. It happens at warmer or elevated temperatures. I think the most well-known is stainless steel in a chloride environment.
Yes.
I remember doing a test a few years ago with 304 in seawater thinking, I'm going to, show stress corrosion cracking. I wanted to get some nice images. So we made up an artificial seawater solution. We stuck in stressed coupons and we started boiling and nothing happened. 30 days later, no cracking. Then another 30 days, so we added additional stress to the coupons. Another 30 days, nothing happened. So then we had to go back to the theory and we discovered that dissolved oxygen also plays a role. So again, you need a very specific type of environment, the tensile stress and a susceptible material. So in that case, dissolved oxygen played quite a big role in that test that I was doing. But one of the nicest examples that I've looked at fairly recently is a failure of brass. Brass is basically an alloy of copper and zinc. It's a solid solution alloy. And in this case, we had a brass tube that's come from a caustic environment. So it's a condensing turbine. And the tube at the top left was actually removed from the bottom of the condenser turbine unit. It was in service for 40 years. The guys at acid cleaned the tubes with sulfamic acid, which from literature we've seen is commonly used. However, during the cleaning process, the alloy showed some dezincification and due to the caustic environment started cracking. So stress corrosion cracking has this branchy cracked nature on the cross-section of the steel. On the lower image to the left-hand side, you can actually see the pinkening of the yellow brass where you see some dezincification.
That's so interesting that actually you can physically see a change in the color based on and sort of evidence of the fact that there is a problem.
Yeah, that's quite distinct with copper alloys. You can actually see within the branch cracking, dezincification within the alloy.
There, that pink is far more obvious.
Yes, again, copper is very, that's one of the examples I like because you can instantly see the difference. With some other materials, you won't so easily see that de-alloying change. This also leads into another type of failure that I've come across throughout my work with Mintek. It's this dezincification and selective leaching. Again, we have a solid solution alloy. Here we have a decorative spoon that was manufactured by our Us artisan training division probably 10
Okay.
years ago at Mintek, and they wanted to clean the spoon to do some changes. And then in the end, the solution they used caused this dezincification or dealloying, which is the selective leaching of the zinc out of the brass. So this is classic corrosion because it's kind of a galvanic effect. So you have your less noble metal that is removed from the alloy in a micro scale. So it's a form of galvanic corrosion. This sort of corrosion, although it's not that relevant here, but it does result in poor mechanical properties. So for plumbing fittings and pipes, they would often use brass because it's a little bit
stronger than copper
copper,
itself.
yes. But they have developed DZR brass and other dealloying resistant materials for those fittings.
That's really interesting to hear that they've actually identified the problem, which is the removal of the zinc, which causes the product to fail in terms of its structural competencies, and have actually developed alloys that don't have this problem. It's quite encouraging. I must say, when I first encountered these alloys, the prospect of the galvanic corrosion happening at sort of micro level, this always struck me as, why did we take the chance? But I mean, we do that in steel anyway with carbon, don't we? In terms of corrosion, we always labor the point, and you in fact made the point here that in the corrosion cell, we're dealing with scenarios that are, always, and I labor it whenever I teach corrosion, we always have 4 components in our corrosion cell. We always have an anode, a cathode, a metal pathway, and then an electrolyte for ionic flow. But there is a form of corrosion that I always feel like it makes a complete mockery of me and everything I know, which is metal dusting, because this is just a form of corrosion that I really don't understand. So could you help explain what is metal dusting and how can it be deemed corrosion in the classical sense?
Yes, corrosion, usually you're looking at your corrosion cell. With metal dusting, it's a catastrophic type of corrosion in environments where you have high carbon activity. So if you're looking at petrochemical or chemical plants where they're dealing with hydrocarbonous or high carbon product, this is where you'll find it. It's more a case of, well, Dion could probably correct me, Dion Slobit. He's done quite a lot of work on this, where you're looking at specific areas in the process plant where you have the specific carbonous or high carbonous environment. And it usually occurs in temperatures ranging from 350 to 800 degrees Celsius. What's very distinct of the materials that do suffer from metal dusting is that it forms like a coke or graphite type product, which relates to the dusting description. Then you have, it's like a specific area. So where the tube would be at a too low a temperature, it wouldn't suffer from metal dusting. So it really, it will just affect a specific band of that process plant of the pipework, which is quite distinct in nature. Stainless steels or a lot of materials are susceptible to metal dusting, including austenitic stainless steels, ferritic stainless steels. Nickel-based alloys have been developed to kind of mitigate the problem. It does delay metal dusting, but it doesn't stop it completely.
You've actually shared a photograph with me, which I think might be quite helpful. So if we have a look here, here's obviously the steel tube, and you can make out in the photograph these pits, and is that where this form of corrosion has occurred?
Yes, this whole sample was from that section, but this nicely shows us the dusting effect. So when they remove the sample from the plant, the dust falls off because it's very brittle and it's quite loosely adherent. So through the investigation, you really have to look at the operating conditions to try and identify the type of corrosion. And with metal dusting, it's extreme oxidation. So on the picture on the right, we have a cross-section of this specific tube. It's called a ferrule, and I think it was austenitic stainless steel, if I look at the microstructure, where you can see on the surface, you have this very thin layer. So the top gray, it looks like cement, is the mounting resin. So in between the mounting resin and the alloy, there's like a thin layer, which is the carbon layer that forms, or the graphite layer that forms. This is often referred to as like a cement type of product. because what happens during metal dusting in the specific environment, the carbon ingresses into the steel. So it then starts reacting with iron to form iron carbide, which is that cementite or cement layer. Then this cement layer then further decomposes to form the graphite carbon, and that falls off as a dust. In the bottom picture, we've done quite extensive work to try and simulate this type of failure or corrosion in the lab. So some of my colleagues have developed this furnace. So we kind of look at the environments and we mix the gases and put them through the furnace, looking at different temperatures and time periods. These are also just 316 stainless steel coupons where you can see the dust that's come off. The coupons themselves still look fairly clean. So the dust isn't inherent. It falls off of the coupon.
So visually, sometimes the steel still looks fine, even when the dust comes off, but obviously it's losing integrity.
This one shows the failure, so the metal dusting at the front end of the tubes that cause pitting. But you can see a layer where, say, the middle tube, it's a little bit gray-white, and then it transfers to black. So if you move towards the back end, the temperature wasn't in the range of metal dusting to occur. So only the front section and a part that has obviously corroded off was within that temperature range. So that's quite distinct with metal dusting, that it only is susceptible in specific temperature
locations. That's fascinating.
A lot of our work at Mintek has gone into trying to look at this mechanism and kind of explore alternatives for use in these type of environments. I know we have a team that is looking at new alloy development for these areas, looking at additions of other materials, chromium, aluminium, silicon, sometimes copper, to kind of control this or retard the metal dusting reaction. Like I've said before, we can't stop it. It's going to happen. It's just to try and reduce the time to failure so that maintenance can come in and replace certain sections. And then again, you would only use this special alloys on those specific areas, and then you would solve the problem. So it's not a question of replacing the entire ferrule tube system, but just the small section. But with those changes, you do have other risks where you can get galvanic reactions between the two tubes and stuff. So this, research is one thing and it's a lot of fun, but in the end of the day, solutions don't always seem practical at first. That's where engineering has to come in to try and find solutions to resolve these problems.
Well, I was just thinking, if it's very specific in its temperature range, then maybe better control of the operating conditions of the plant could prevent this, unless the production has to happen in the temperature band.
At a higher temperature. Okay. So as the fuel gas comes out of the furnace or the specific process, these ferrule tubes, it's a condensing system, so it cools down.
Oh, I see.
So
okay.
The corrosion actually happens at a lower temperature to where operating temperature is. The solution will probably be to run everything hot all the time, so we're outside that range, but that's also near impossible. So that's why
and costly.
Research to try and retard the corrosion, because we know it's such an extreme environment. To try and mitigate it, it's horses for courses. You find a solution that is useful now. Currently, I think most guys are still using stainless steel. They know there's metal dusting. They just perform maintenance on a fairly regular timetable, and that's how they're mitigating it currently. So, with the research, we try and look at pie-in-the-sky solutions where we can resolve those sort of things. And metal dusting is something that Mintek has looked at for many years.
It's an interesting phenomenon because I recall my first exposure to it was probably only about 10 or 15 years ago. And I felt that it was almost a new form of corrosion that had appeared on the scene. So I wonder if it's been happening and other things have been blamed for the failure of various components before they were able to identify the large contributors to the metal dusting format.
Yeah, I think you're right in a sense, because a lot of the coke falls off. I think many people have probably noticed the pitting, but have never really associated with metal dusting until someone had the idea. Often you see, maybe it's not a new form of corrosion, but possibly a better understanding of the corrosion and its effect or relation to the environment. So a lot of corrosion is very connected to the environment it's in. A metal will react differently in any different environment. And that comes to material selection. So once you start changing the environment and you're able to do that, you have to look at your material selection on an atmospheric case as well, if you're indoor or outdoor. But yeah, and a lot of process environments you don't fully understand. So how long did it take them to realize, listen, the temperature range within those tubes is between this and this? All of that plays a role. And I think it takes a lot of smart people to figure those mechanisms out. And then we read about them later in papers and journals.
Exactly. And it is interesting. I think also in general, environments are becoming increasingly harsh. And so rare occurrences of corrosion are now becoming more common because the general environmental conditions we've increased temperatures to increase productivity, or we've got higher levels of pollution, which causes its own problems. And I think there is something that, corrosion is not what it used to be, which is 100% correct, because the environment is increasingly becoming more challenging in every regard.
I also think that a lot of investigators have become aware that to share information, when a specific company is suffering from, let's say, some kind of problem, in the past they didn't share that information because it would make them look weak. So, the last couple of years, we've learned a lot from that, because a specific company, you're not the only one suffering from this issue. And then actually working together, which is easier said than done, would help to resolve a lot of problems.
Yes.
But in the end of the day, they're protecting their product, they're protecting their process. So it's also sharing and understanding of the science and things around that. But also from a business perspective, I think other things come into play.
I think you're absolutely right. Gosh, Melanie, you really have been exposed to and have helped us to experience such a wide variety of corrosion failures. So thank you. As we start drawing to a close, you've made a couple of comments through our discussion about how we can work to find optimal materials. Can you talk about some things we could do if we're exploring a new process? Some of the things we could do to see whether a material is likely to withstand what we want to subject it to?
I think one of the basic examples I can give you is in the mining industry, we deal with a lot of slurries. And from that, we've kind of seen a lot of failures, especially where slurry rates change and then you have flow assisted or erosion corrosion. Now, we had a few clients that had these issues and wanted to look at better material selection for their solutions. Some of them have made adjustments to that, but found that a lot of the metals aren't suitable. So this opened up an area where we started looking at linings or lining materials. Now, for a metallurgist, this is it's like a hardcore pain. So it's not really my industry. But I mean, what we try to do is we try to develop a test that they could use to rank and compare their materials with the standard steels and metals that they were currently using. So we took a few standards. Dion Slabbert as well worked with me on this many years ago. At Mintek, we developed a test that helped with wear testing specifically for slurry solutions. So it's kind of based on a sandblaster type mechanism. So we were blasting the slurry on the samples. And through that, we also looked at blast angles and the rates and how they interacted with the type of erosion or wear. So you had impact erosion and you had linear flow type corrosion, so it's more drag. I think I've got a photograph or two of the test vessels. On the left, we have the vessel from the outside with the slurry pump. So at the center, you can see the slurry inside the vessel with a stirrer. So we obviously have to stir. That was one of our biggest challenges because these slurries have such heavy solids. We had to keep all of them moving. So our sample is actually put within that little block on the side of the vessel. And I've got two samples on the side that shows the different types of wear or erosion that we were creating. So with the blue one, again, it was a paint type environment. We had a more impact. So the angle of the nozzle, actually, sorry, I don't have a photograph of the nozzle here, but it was more at a 90-degree angle, and it gave us a deeper, more isolated type of wear, which we would see in some instances. So maybe in a tube bend, or where the pipe diameter decreases, so we have that increased flow. But then we also looked at a different type of flow, which is the bottom sample, which was more a flatter angle, which represented more the drag or sliding type wear. And with this development, we actually tested hundreds of different lining and coating materials for the mining industry to try and understand or rank and compare them in these two different environment. But the biggest challenge, any corrosion test where we're trying to simulate reality, it's very difficult because there's so many other aspects at play. It just helps us to rank a material with another, looking at the science. But, service in the end of the day is the most important. And there's so many factors. You can't control all of them or test for all of them. So
absolutely,
doing some tests gives you a little bit of an upper hand.
Well, Melanie, thank you. And thank you so much. Gosh, I'm sure our audience's heads are swirling like mine is with all the information you've shared with us. It's been so interesting and so informative. So thank you. I feel as though we've hardly, dare I say, scratched the surface, but I thank you that you've been so willing to share your passion with us, to share so many different types of failures with us, and some useful tips on how we can possibly test materials for future use. Thank you.